Hello and welcome back to this course, and today we are going to look at a simple predicting machine. In other words, this is going to give you a very basic understanding of what a predicting machine is, and later on we are going to see what is classifier as well. And having these two backgrounds, you are going to have a better platform to understand what is a neural network. And later on we will see how we can expound on that concept of neural networks into other deep learning methods. So as I told you, today's subject is just a very basic predicting machine. So as far as computing system is concerned, we like to always have this process. Like what we have is, like, we have an input, and then we process it. Let me clear this off. I'll do one thing. Let's put this over here. Okay, let's start a new. So when you have an input system, then you have a processor, and then you have an output. So let's call this as the input, this as your output, and in between there is some kind of process going on. So this process can be anything. It can be a simple, say, simple calculation, right? Let's expand on this aspect. Let's say that we have, let's say you have like 3 cross 12, and what is the process that's going on? Maybe just imagine there is a calculation. So 12 plus 12 plus 12, and your output is going to be 36. Well, it's a very simple process, and at times this process can be used to make certain decisions, or it has to think as it proceeds. Okay, now let's look into a better application. Let's consider you're having a similar system in which you're going to have the input as say kilometers, and let's say you have to calculate this one, and you are expected to have an output, and you want the output to be, say, miles. So you have to calculate this system, and for one thing you are sure about this kind of process is that you know that there is a linear relationship between kilometers and miles, or miles and kilometers. Like when you increase the kilometers, the miles will eventually increase, and when you reduce the kilometer, the miles eventually would reduce. So what we are going to have here is, we are going to have a simple relationship for miles. Like let's say miles equals kilometer times c. Let's say c is a constant, and we don't know what is C yet. So this is the only clue that we have right now. So with this real world application, let's try to see what are the true values that you have for this situation here. So let's try to find what is the truth, or in other words, it's kind of a truth table for this particular application. You have kilometer, and you have miles. Well, now let me put it as a table so it will be easier for us to check. Okay, anyway, let's do it properly. So coming back to this true values, the first true value we are sure about is that when kilometer is 0, your miles are also 0. The second true value you are sure about is that when you have like 100 kilometers, you are going to have like 62.137 miles. So this is what we have here. So let's, as we know, we don't know the C over here yet. So let's try to start with a certain random values. Let's start with some random values for here. So let's say we know that miles equals kilometer times C. So here the process that you are going to have here is times C. So let us try some values here. Let's say C equals 0.5. Let's say C is 0.5. So what happens at this moment? So you're having, say, 100 as your input, and you know that 0.5 is your C value, and your output is going to be 50, right? Okay, so this is our first observation, the initial observation. We got this result. So based on that, this is not bad, because our value that we chose for C is 0.5, and now we can actually find the error between actual value and the value that we got. So from the second true example here, from this example, we come to know that the actual value is supposed to be 62.137, but we have an error here. This error can be written as error is the true value or truth minus the calculated value. Okay, calculated value. So here the true value is 62.137, and your calculated value is, say, 50. So your error that you got here is 12.137. Well, this is your first try. Now let's see. We know that we are shortage of 12.137 miles. So which means that, and we do know that kilometers and miles have a linear relationship. So with this in mind, what we can do is that we can increase the value of C so that we can try to obtain a more closer value, that is the true value, the more closer to the true value. So with this thought, let's try to do again the whole process. Say you have this kilometer as your input and your miles as your output, and we know that what is going on inside. Miles equals kilometer times that C value, and initially we had 0.5, right, and we got some error. We know the error over there. So now let's choose the C value to be say 0.6. Let's say the C value is 0.6, so which means that K times kilometer times 0.6. So what happens at this moment? Your input is 100 and your output is going to be 60, right? So right now you got the correct. Let's calculate what is the true mile values, the true value that you have here. Or truth that we have here is 62.137. Now you can check again what is your error value. Well, when you try to check it out, you can see that error again is true minus the calculated one, which is got 2.137. Well, what we did now is that we have reduced the error for this particular problem. In fact, we have reduced error to a huge extent. Now it's 2.13, the error. Well, we still know that we are shortage of the true value, so which means that we have to still increase and see what is going to be your output. Let's try again. Let's take, for example, you have the input as kilometer, and you know 100 kilometers is given as the input, and you want to see the output, which is calculated miles. Okay, so again miles is kilometer times C, right? So this time let's increase to 0.7. Let's increase the C value to 0.7. So when increase to 0.7, what happens there? The output becomes 70. And we know that from this observation we can clearly see that 70 is more than what we need. So it's better for us to check the error and see how much that is for. In this case, the error would be 62.137 minus 70. So this will be like say minus 7.86. Yeah. Okay. So right now we know that this is too far. So we often call this kind of scenario as an overshoot. This is like overshooting of error. Error is in fact increasing, right? So we call this is the overshoot. So but at this time we have come across an important concept in machine learning, especially with respect to the things that we are going to learn about neural networks. Let me briefly explain what it is. So we know that we want to achieve zero error, right? That is our target. We want to achieve the target. In this aspect, we have to achieve this 62.17. That should be our target, which means that we want to get an error to be zero. That is our goal. But every time when we try to put a random values, initially we had a random values, and we know that it is a little bit different from what we expected. So we increased the value. Then we got that error has reduced a bit, right? So you found that the error has reduced a bit and a bit and a bit, but all of a sudden it again shoots up, right? So this aspect of what is happening here, it's reducing a bit, but suddenly it shoots up somewhere. It goes somewhere over there. Okay. So our objective is to reach this goal, which is our minimum error. So we will talk about this aspect of the so-called reducing the error or finding the global optimum values later on. But for the time being, you just understand this idea behind what we are doing. We are in fact trying to reduce the error. As we try to reduce the error, we found that at times it can shoot over, right? Then you have to come back again. So that's what we are going to do here. Concept, we call it as gradient descent. So anyway, we'll continue with this one and see what is going to happen next. So with respect to what we have seen here so far, let's try to reduce the error. So we know that it is an overshoot, so which means we have to make sure it should be less than 0.7. So in this case we had a 0.7. So we know that it should be less than 0.7, but it should be more than 0.6. And let's try again. So this time let's try input as 100, and your C value is miles equals kilometer times C. That is, let's take it as 0.6, say 0.62, and your output going to be 62. Now what is the error that we get? We get this error as 62.137 minus 62. So this is going to be your error. So that's nothing but it's going to be 0.137. So in fact we have drastically reduced the error. This process, by step by step trying to reduce the error, we are in fact doing several iterations. You are repeatedly doing this one after another to achieve the target. It is kind of an iteration that we do here. So let's go further and examine more about the whole matter. Right now what we did is about building a predicting machine, right? So when I say predicting machine, we are trying to see which is the best value for C. In other words, we are trying to predict the value for C that would fit our model. So in other cases, in different scenarios, we try to classify things. When you have two elements, or if you have two features, then you want to classify these two elements. In machine learning, there are a lot of classification problems we may come around. So sometimes we refine the prediction by adjusting internal parameter, just like what we did. We know that error, so we try to do it by for a prediction problem. Now we are shifting into a classification problem. Classification is quite different from predicting. Let us see an example. Okay, let's take this example here. Length, width, and we are going to look at two classification. Let's say we have this list here. And we have another one. Okay, so let's consider this as our locust, and let's consider this as a ladybird. So we are going to see the difference here. So width versus length for a certain, say it can be a garden bug. So we have to see how we are going to classify the same thing. So unlike the predictor problem where we try to predict the values in case of the correct number of miles for a given kilometer, we are trying to adjust a linear function. We know that they are kind of linearly related. So the linear function actually gives you the straight line, and when you plot their line against the input and output, you can see how we can adjust the parameter and try to find the slope actually. So the adjustable parameter in the previous example was C. We try to adjust the parameter. So when you adjust the parameter C, it changes the slope of the straight line. Initially we try to have say 0.5, then 0.6, then 0.7, and then 0.62, so on. So that's a similar approach, but we'll see how this can be done with respect to the problem that we are facing right now. Let's try to have a straight line here. So if you have a straight line just like this, does this straight line, or can we call this as a line that separates two classes? Can we say that? No, we can clearly see that it's nowhere separating the two classes like locust and ladybird. In fact, it goes into the locust. Only maybe a couple of locust has been classified on this side. The others are on the other side of ladybug. Okay, if that is the case, let's remove that one. This is not a good one. Now let's go for another option. How about this line? Can you call this as a proper separating line? This is more worse, right? It's not even dividing even one element. It seems that all the elements are in the same class. Okay, let's remove this one as well. How about this one? Well, this is in fact is quite good because it clearly separates the two bugs, the locust and the ladybird. So you can clearly say that this is in fact a perfect classifier. Well, given these conditions, we can classify any bugs that are coming in. Suppose you already have this separating line. Once you have this line in picture in place, if there is a new bug comes in with a certain length and certain width, you can clearly see that this falls in which category, either on locust side or on a ladybug side. Just like this scenario here. Once this has been drawn, if a new bugs come in, suppose if this is unknown bug, if this comes in based on the given true values of width and length and the place where it falls, you can clearly see that this belongs to a certain class. Even if you have not seen this data before, once it comes into the place, you can clearly classify. Now let's try out an example of training a simple classifier. We are going to train a simple classifier. Right. Let's take these examples. In fact, let me put it this way. Okay, let's write it as like 1 and 2 with 3.0, 1.0 length. Okay, so this is the given thing. So in this example, if a bug has width as 3.0 and length as 1.0, we supposed to have this to be ladybird. And if it is longer, like length is 3.0 and it is thinner with width as 1.0, then you are going to call that as a locust. So this is as a simple example here, which we know that these are true values. So it is this example which helps us to refine the slope of the classifier function. So example of this true value we are going to use to teach a predictor or a classifier. We call it as the actual training data. These two are the basic training data that you have in hand. So let us examine this whole features of training information. So what we have here is simply either a caterpillar or, in fact, it is a locust, right? We have a locust, or what color we are using here for the green. So let's use, oops. This is the lady bird. If it is length is more and if width is less, we call it as a locust. If width is more and length is less, we call it as ladybird. Yeah. So this is the training data. In fact, we have, right? So we can call it as, these are the training data that we have in hand for classification of bugs, let's say. So this is the problem that we have right now. So let's start with a random dividing line. So we don't know exactly where the dividing line is. Let's start with the random values, just like we started with the random values for the miles and kilometer predictor. So we had a linear function whose parameters are adjusted in the past. So we can do the same thing. We can have a linear relationship. So for this linear relationship, let's write it as y equals ax. So here we know this y equals ax is very simple term, and the original term may be like y equals say ax plus b. Maybe you might be familiar with another term where we say y equals like beta naught x plus beta 1 for some linear relationship. So we assume that in this case, we assume that the dividing line actually passes through the origin. So we don't have this term, we don't have the term b. We want to start the whole process to be very simple, and based on this we are going to analyze the whole thing, how we can use it. So right now, as we have seen before, in this example, you know what is x and what is y. Both are the values in the graph, right? The length is your y and width is your x. So what is a? So a is the actual control parameter that decides the slope for us. Okay, let's start with some random values for a. Let's say a equals say 0.25, just to start with, and the dividing line we are going to have is y equals 0.25 times x. And if you try to plot a graph for this given thing, so you can see what is happening here. So two training data that you have is this one. Okay, so coming to this problem here, the training data that we have in hand, and your y equals 0.25 times x, right? So we see that this line y equals 0.2 times x is not a good classifier, because as we can see clearly, the line does not divide the two groups. So if the bug is above the line, then it seems to be like a locus, right? This is called locust. So maybe all things are classified as locust. We don't want that to happen. So we will just want to make sure that we try to rearrange things so that we can have better values here. So again, as with the previous example, we can try to find the error. So what is the error? What is the fault in this line? We try to rectify this fault and see how we can do it. So we want to see if we want to do certain thing repeatedly, as before we had iterations, right? We did repeatedly. Like that we can see whether we can do certain repetitions to avoid the whole stuff. So okay, when it comes to the same problem here, we have y equals 0.25 times x. So if you want to consider for a value of x, let's say it's right now we are this item, we want to make sure that Right now this line is near this one, right? So we want to make sure that it has to go over this bug. So at least if you say, for example, if I have y equals say 0.25 times 3.0, so 3.0 is the actual value of x for that bug there, the ladybird, this one, right? So if you have this, it comes around 0.75, and from this we know that one thing is for sure that we have here is the function with this parameter a. Initially we started with a random number which is 0.25, and we come to know that for this 0.25 with the bug width, this is the bug width of 3.0, we got the length as 0.75, because that is your y, right? Y equals 0.75, which is the length, actual length. But it is kind of small for us, because we know that the actual length of that bug is actually 1, right? If you look back, for the ladybird the length is 1 actually. So if you put 0.75, what happens is that the line is going to directly pass through that ladybird. So that's where we have to see what kind of error is happening right now and how we can avoid things. So we should make sure that this y is equals 1.0 for the ladybird, we know that. So if you want the line to be over this ladybird, we need at least y equals 1.1. At least it has to be 1.1. Then you can ensure that this line will be over the ladybird. It can be 1.2, it can be 1.3 as well. But one thing we can be sure that it cannot be 100 or 1000, because from this example it is very clear that 1.1 is quite reasonable for this scenario. Now let's try to calculate the error based on this 1.1. So error is again, we can call it as desired target minus actual output. So in this example we have gone for 1.1, and before we had as 0.75, so that takes us to 0.35. So now again you can think a bit and remind yourself of what is actually happening and think about the error values. So we had this line which is 0.75, and this for 0.11, which is a desired one, we wanted to have it, which would be like this line, and the actual error that is happening here is between these two elements. So we know that this is the line for the calculated value. Which is 0.75, and this one is desired value. Okay. Okay, now, so what do we do with this error E? In fact, the error E has to guide us to get a better refinement of A. So we have to go one step back and think about how this is going to happen. So we want to use the error in Y. So this is Y and X. Okay. So in this case, the error we call it as E to inform that there is a change needed for the parameter A. So to do this, we need to know how two are related and how is A related to E. So we have the value for A, right, if you recall, and now you can think about how this A is related to the error E. So if you just come to know about this whole process, we can easily understand how things are changing. And if you go a little bit backwards, you know that Y equals AX, right? This is where we started for a linear. This is the linear function for a classifier. Linear function for a classifier. So with this thought, we already had an initial guess for A, which is 0.25, and we know that for the initial guess we got a wrong value for Y. Our actually the Y that we got is not suitable. So now we need to check. We want to correct the values. We want to have a desired value. So for the target value T. So let's consider this target values, or in other words, the target or the desired value. Based on that, let's try to explore more of it. So let's call T equals A plus delta A times X. So here what we did is to get the value of T, we need to adjust the value of A by a small amount, a small change. So just we use this delta symbol indicate that a small change is needed. So we are writing it this way, and you can also picturize the whole thing so that you can easy to understand. So what we're doing is almost the same diagram. I think we can go back to this diagram, and I would relate the same thing over here. Let's call it as maybe I will use this color. So this is nothing but this line which is calculated, Y equals AX. This is what we used before, but in order to get the desired value or a target value, we call it as T. What we have to do is like A plus delta A. There's a small change in A is required times X. Right, this is what is needed from the given part. So let's go further and see how we can expound on this. So remember, E is the difference between the desired value and the one that we calculated, right? So here are again the current guess for A we have for the error is t minus y, right? You can look back and check it out. T minus y is your error, and that is nothing but A plus delta A times x minus ax, and further you can expand the whole thing. So you have E equals same t minus y equals ax plus delta ax minus ax. So finally E is nothing but delta ax, right? Delta A times x. So it's quite remarkable. The error E is related to delta A is a very simple, it's a very simple thing that we have seen so far. So it's very simple, but we can see how things are corrected one by one. A simple relationship makes us to have everything in order. So let's go further. We want to know how much to adjust, right? This delta A, how much you have to adjust, or how to improve the slope so that you can have a better classifier. So let's put this further. Delta A is equals E by x. So this is a very simple expression that gives us an idea how to get this change in A, right? So we can use E to refine the slope of A of this classifier that we are talking about. Yeah, that's what we have to do. We have to update one by one. Okay, let's go back again. How about the error? Initially the error was 0.35, right? The error was 0.35. If you look back again, the error was 0.35 for the given input 3.0 width, right? So just keep that in mind. With this in mind, we can consider delta A equals, what is the error? Error is 0.35. And how about the width? For the width, you had a point, it is actually 3.0. Yeah, so if you calculate, you get 1.1166. Okay, so this means that we need to change the current value of A. We know the current value of A is 0.25, and this is the change in value should be 1 point. In fact, it's not 1 point, it should be 0 point. I am making a mistake. Okay, 0.1166. So we need to have this, we need to improve the value for A, right? So A plus delta A is, initially A is 0.25 plus the delta A we have to have is 0.1166. So this gives you, say, 0.366. Let's put it as 67. Yeah. Now then calculate the value for y with a new value of a. So new value of a is 1.1, right? If you recall, we wanted to get the new value of a, which is 1.11. Okay, so let's see and try to calculate things for 1.11 and see how everything works out. So we also have to make sure that this training example, we are going to learn one by one how the actual true values are really matters to us. So the true values, for example, in this example we have x is 1.0 and y is 3.0. So those are the true values. So you have to check what happens if you put x equals 1.0 in the linear function. So we already know what is your new value of a. So the new value of a is, you're going to add a plus delta a, that is 0.3667, right? So that's going to be your new value of a. So with that you're going to see the x value should be new value as well. So let's say y equals ax, the same formula, but here we are going to use the x value as 1.0 and a value is 0.3667. So this actually gives the same value, right? When you do 1.0 times 0.3667, that is 0.3667. Same thing, that's it. Okay, but if you look at the value of y, the actual value or the true value of y that you have here is 3.0. But according to this one, the y is 0.3667. So that's a problem right now we have. So we have to try to see what is actually happening here. The way we did before, we can also do the same thing right now. The thing is, we want to make sure the line does not fall on the, say, locus itself. So this is, as you can see from this given problem, x as 1 and 3.0 is a locus. So we want to make sure that it doesn't fall on the particular thing. So let's try to calculate the error here. So at least you want to make sure that it is 2.9, right? We had 3.0, which is exactly on that one, but we want to make sure that it should be lower than 3.0 to make sure that we have a classifier. So here 2.9 minus 0.3667, that's going to be 2.533. Yeah. So we got a big error here, and we have to make sure that this linear function has to learn from simple training example. So we can see that the line towards the single example is being driven force. So let us update this a again, try to update this a again and again. We know that again, like delta a equals e by x, so which is again this part is like 2.5333 by 1.0, which is again 2.5333. So this means that we have a new value for a, the new value for a. So let's say a equals 0.3667 plus 2.5333. So that is almost like 2.9. So that means x equals 1.0. The function gives 2.9 as the answer. When x equals 1, you get the answer for the function is 2.9. So which is in fact the desired value, right? 2.9 is in fact the desired value, and it is kind of fair enough for us to understand the whole concept here. So let's try to plot the whole different training things that we saw. So initially we had y equals 0.25 times x. Then we had a first refinement. We refined y equals 0.3667 times x, and final refinement y equals 2.9 times x. So when you see this plot, we don't seem to have improved the slope in a way that we hoped, because the way that we hoped was like at the center of the two groups, right? So anyway, we got this answer right now, so we can update to get the desired values for y. Anyway, what's wrong with this right now? Well, if we keep this doing updating for each training example, we get that the final update simply matches the last training examples as close as possible. So we might as well have to not bother with all the previous training examples. In effect, we are throwing away any learning previous training examples might give us and just the learning from the last one. So that is one of the problem people used to have. So initially we had one, and then you refined, and finally you have the final refinement. So we want to make sure that all the previous learning examples should not be ignored. Well, that is very important for any machine learning concept. So we have to moderate the updates. That is, we calm them down a bit instead of jumping into the conclusion that the final refinement is your correct answer. So we have to make sure we take each fraction of any changes that delta A is giving us is not the final output, final answer. So in this way we can move in a direction of this training this example, so that we can cautiously make sure that we come up with potentially a better solution. So let's think about how to moderate our refinement, and then let's see how this thing is actually related. So you can again think about what we did in the previous example, like miles and kilometer. We know that they are linearly related, and you know that once you increase the c a little bit, what eventual changes that are happening. If the change is more, then you are going to reduce the value of c. So that's the same idea. It's a very powerful mechanism in which you are going to change. So this moderation of change that you have, at times it may have some side effects as well. So when training data itself can't be trusted to be perfectly true and contain errors or noise, both of which are normal in real world measurements. So moderation is the key factor. Try to smoothen the whole thing. So right now let's try to do the whole process again, or in other words, let's rerun the entire thing. So let's call here delta A equals L times E by X. So this moderating factor L, we can call it as the learning rate. This is the learning rate. And let's call the learning rate as L. L is going to be a learning rate. Again, let's pick up random values here for the learning rate. L, let's take L equals, say, 0.5, just to start with. So it simply means that we only update half as much as we would have done without any moderation. So let's run through this again and see what happens. We know that initially we start with A equals 0.25. So the first training example, you had Y equals 0.25 times 3.0, which is 0.75, right? And a desired value, we are talking about, we had a desired value of 1.1, which gives an error of 0.35. So you had a of, the Y is 0.75, but a desired value of, we had 1.1, right? Value of Y, desired value of Y is 1.1. So in that case, we had the error of 0.35. That was the error initially. So let's take this into account and let's look at this delta A equals L times E by X, which is 0.5 times the error is 0.35 times 3.0, which gives us 0.0583. Okay, so now we got this value. So now let's update the value of A. So this is delta A, right? Now let's update the value of A. A is 0.25 plus 0.0583, that is 0.3 0.083. So this is what we got right now. So right now we have the new value for A on this training example for x equals 3.0. In this case x is 3.0, and we get the y equals let's put this out. For x equals 3.0, we got y equals in this case 0.3083 times 3.0, right? A times x. So this is going to be 0.9250. So that is your value of A. So the line falls on the wrong side again if you check for y is 0.92, because we know that it is below 1.1, because the desired value is 1.1, but this is still below the value of 1.1. Anyway, but this is better than the previous one we had. We had 0.75. It's better than that one, which means that we are in fact on a better or on a right direction to find the solution. So let's continue the same line of thought, and let's try to use a similar vein and see how it applies for another training examples. So this is the first training example. Let's go for the second training example. For the second training example, x is equals 1.0, right? So A equals 0.383, and we have y equals 0.383 times 1.0, which is 0.38. Okay, I think I made a mistake here. It should be okay. It should be 0.3083. 0.83. Okay. So now you got this value here. The desired value was 0.9, so that the error is we got this values here. Desired value of let's consider we have the error to be 0.9 minus 0.3083. That is going to be 0.5917. So there again delta A equals L times E by X. That is 0.5 times 0.5917 by 1.0. So this will yield us 2.958. So this is going to be your delta A. So what is your new A from there? Now the new value for A equals 0.3083 plus 0.2958, which is going to be 0.6042. Now we can try to visualize the entire thing. Let's have the same examples here. Locust. Initial first one we had here. So next we had a moderate refinement. Then the third one we have somewhere here. Initially y equals 0.25 times x. We'll put it this way. And this is final moderated refinement. Okay, so that's all we have here. So therefore, accordingly, what we have here is a simple learning mechanism. We started with y equals ax, and finally we found the value for a equals 0.6042. So this is a good dividing line. That's what we understand. So this is where I would like to stop this lecture, and we'll continue on learning how this classifier actually works, and what is the next level of classification, or what are the problems that people face when you have such classification. Let's look at this scenario with a training example of real worlds. Training examples in real worlds can be noisy or contains a lot of error. So moderating updates is very helpful, and it can have a very deep impact on the actual classifier. So that's all I'd like to share with you for today, and let's stop our class here, and I'm looking forward to catch up with you in the next lecture.